Find sine of negative 510. Whenever you have a negative angle, you might want to use the even and odd properties for trigonometric functions. Well, so recall that sine is an odd function, that is, it's symmetric about the origin and it meets the condition that f of negative x equals to negative f of x. In other words, that negative sign will go outside of what's that, of the trigonometric function. That's negative sine of 510 degrees. The thing here is, clearly this angle goes beyond one rotation, that is, it's an angle larger than 360 degrees or 2 pi. Well, so my advice here is to break up the angle 510 degrees as 360 degrees plus what number is that going to give us? What's that? 510, is that 100 and what? Or actually, so is that a 210? 210 maybe? Well, I got something else here. Well, you know what? Let's stick to the negative version, or no? Let's still do the. Let me get my calculator here. So, because he did something weird on the book. So 510 minus 360 groups, and that equals 150 actually. All right, so that's actually 150 degrees. And well, since this angle 510 degrees, it's a coterminal angle for 510 degrees, we can write this as simply negative sine of 150 degrees. All right, now here is where we need to look at the location of this angle. And well, 150 degrees, I believe it's an angle below 180 degrees, and this angle is actually in the second quadrant, right? So that's 150 degrees. Well, we need to evaluate this this trigonometric function using the reference angle. How do we get the reference angle? The reference angle is obtained by it is the angle formed by the positive x-axis and the angle formed by the ray that we go starting from the standard position. Well, in this case, it's this acute angle. So since 150 degrees to 180 degrees, we need 30 degrees, right? So 30 degrees. So in this case, we are going to evaluate negative sine of 30 degrees. However, we need to be very careful because we need to make sure that the sign of the sine function is maybe positive or negative in the second quadrant. Well, it's all students, take calculus, so sine is positive in the second quadrant, but we keep this negative. This negative is kept from the fact that the function was odd. So sine of 30 degrees, I believe, is negative 1/2 in this case. All right? Well, I know the y is positive, but the negative actually comes from the fact that the function is odd. All right. So let's see. Another kind of problem, they're giving us the value of a trigonometric function here. Sine of theta equals negative 4/7 and cosine theta greater than 0. So we need to interpret these two pieces of information. They're asking us to find or to evaluate cosine of the angle and tangent of the angle. So first of all, let's refer to the Cartesian plane. All right? And recall that all students take calculus, all right? And then in this case, number one, we have a sine function that happens to be a negative value. I don't care what those values are for now. I know it's 4/7, but we'll bring up the number soon. However, sine is negative at which quadrant? Or at which quadrants? Actually, there's two quadrants in which the sine function is negative. Which one is it? 3 and 4. All right. So 3 and 4. Sine is negative and sine is also negative. Now, we need to choose one of those two quadrants, 3 or 4, the one that has a cosine greater than 0. In other words, the one that cosine is a positive value. Which one is it, the third or the fourth? The fourth one, right? Now, since sine is, what is that? Opposite over hypotenuse using SOHCAHTOA. In this case, check how the opposite to the angle is the -1. So this -4 over 7 means -4 divided by 7. It's not the 7 taking the negative sign. In fact, the hypotenuse is never ever negative. Only the sides, either the opposite or the adjacent wall, and that depends on the orientation based on the Cartesian plane locations. All right. So from here we can write down the elements of this triangle, -4, 7. We need to find the length of the adjacent side, and for that we would use Pythagorean theorem. A squared plus b squared equals to c squared, where a is given, or could be b, either way. It doesn't matter. It's addition. And that equals to 7 squared. All right, so that's 16 plus b squared equals 49. And b squared equals, so 49 minus 16, 49 minus 6, that's 43, minus 1, that's 33. That's 33. And b equals the square root of 33. And I know it should be plus or minus square root of 33, I agree, because that's the correct use of the square root property. We get two solutions, we're solving a second degree equation. However, in our geometric context, check this out. Notice this x right here, which is root of 33, is going in the positive direction of x. Otherwise, if we had our triangle over here, then it would have been negative root of 33. However, it's not the case. All right? So in this case, no need for the plus minus. Or if you want to be more explicit about it, keep it and then just note that take the positive, the plus 1, since x is going, or x is in the positive direction. All right? That's only if you want to be a little more explicit, and so you can have a better understanding of why do we take the plus in this case. All right, now that we have the three sides of the triangle, we're good to go and evaluate cosine, which is adjacent over hypotenuse. That is the square root of 33 over 7, and no need to do anything else in here. No need to rationalize any denominator. One last thing here, evaluate tangent of theta. And well, in this case, tangent by definition, that's opposite over hypotenuse. Opposite, which is -4 over the square root of 33. And well, in this case, we don't like radicals in denominator. So how about rationalize the denominator by multiplying numerator and denominator by the square root of 33. And well, that's -4 root of 33 divided by root of actually just 33. And that's final answer for this example. Yes?
Is it tangent opposite over adjacent?
Over adjacent, opposite over adjacent. Yes, Yes. But still, I got the right numbers, I think, right? Anyway. Yeah, thank you. All right, let's see. So there's a couple of ways to go about this kind of problem. So number one, we use the Pythagorean theorem to get the missing value, the missing length of the triangle here. However, we can also use trigonometric identities, and well, let's do a similar example, but this time using the identity. So we are given cosine theta equals negative 3/5 in quadrant 2. So in this case, they're explicitly telling us quadrant 2. They're not telling us like cosine greater than 0 or the like. And they're asking us to find sine and tangent using trigonometric functions. All right. So, number one, quadrant. Let's go to quadrant 2. And let's draw a point or an angling, whatever that is. Well, in this case, cosine theta, which is negative 3/5. Well, the hypotenuse is never ever negative, so that means the negative goes to the 3 and the 5 goes to the positive. That is 5, which is the hypotenuse, and negative 3, which is the negative 3. Well, actually no, we're not going to do the, well, okay, that's fine, we can do that. So in this case, we're going to use trigonometric identities, and well, so since in this case they're giving us cosine, how about we use one of the identities to find out what the sine function is given cosine? Well, if we use the reciprocal identities, well, since we were given cosine, the reciprocal is secant, but they're not asking us to find the secant function. Is there any other alternative? Well, how about using the quotient identities? But we only know cosine, we don't know tangent, we don't know sine. Actually, those are the questions, sine and tangent. All right? And in this case, well, how about we use the Pythagorean identities, because in this case, sine squared plus cosine squared equals to 1. So sine squared theta plus cosine squared theta equals to 1. We know that cosine, well, sine squared theta plus quantity cosine squared, which is negative 3/5, equals to 1. And from here, we may go about solving for the sine function here. So sine squared theta equal, or plus rather, 9/5 equals to 1. Let's subtract 1 from both sides. That is, or 9/25 actually. And sine squared theta equals to 1 minus 9/25. And sine squared equals to 25/25 minus 9/25. That's a 14, or no, 16. 16/25. And then solve for the sine function here. Sine theta equals plus or minus the square root of 16/25. Yes, let's keep the plus or minus for a second here. There's a reason why we need to keep it. Well, sine theta in this case, notice both the 16 and the 25 are perfect squares, so square root of 16/25, that's 4/5. Now, in this case, which one are we going to take? Are we going to take the positive or are we going to take the negative? Why is it the positive in this case?
Because quadrant 3, the x's are only negative.
And y is positive, right? And y is the sine function, right? So take the positive since sine is positive in quadrant 2. All right, that's why we would take the positive one. All right, so in this case, sine sine theta equals to 4 over 5. And I think we have all the information to get the tangent function, because if we use the quotient identities, we know that tangent theta equals to sine theta over cosine theta. And we know those two values, that is negative, or actually positive 4/5, which is the value of the sine function, and negative 3/5 for the cosine function, negative 3 over 5. And well, we have a complex fraction. Here we have a fraction being divided by another fraction. So 4/5 times negative 3 over 5. We can divide, negative 5 over 3 actually. And we may actually divide out the 5s. And that's negative 4 over 3. Right? Final answer. I mean, it looks like the same thing as we did. I mean, because essentially, since this is a Pythagorean identity, it's the same as using the Pythagorean theorem to find the length of the missing side anyway. It's just that instead of using A, B, and C, we're using sine and cosine instead. But essentially, the kind of work, it's not different from it. All right? And I believe this is the end of the section, actually. So let's move on to section 4.5. And section 4.5, I think I got it here. All right. So today we're going to look at graphing sine and cosine functions. So no more finding values of trigonometric functions. Well, they're going to be there somehow. But it's not like we are going to be computing them and referring to the unit circle every single time or to the reference angles. All right? So, let's see what the graphs of y equals sine and cosine look like. Well, number one, if you've seen this before, these are also known as wave function or oscillating functions. That's because these functions just go up and down, oscillate between -1 and 1. They look like waves. They're used in a lot of applications such as wave motion and electronics and signals that go, those signals bounce back and forth between a value or another value. Well, and the most generalized version of the sine function is this one. And actually, this graph right here is showing us the graph of the sine function over one period. So it's the one that I will highlight here, right? So that's the sine function over one period. And well, you might remember how the unit circle, or well, yes, angles around the unit circle or a circle of any other radii, the angles repeat every time we add 360 degrees. So if we are at a location on the xy plane, that's a point on the circle. If we add 360 degrees, we should fall in the same point a second time. Add another multiple up to pi and you will keep falling in the same point. So that's what these dashed lines or dashed curves represent. The fact that this goes on forever in the positive direction, in the negative direction, infinitely many times. And well, we have these key points. I mean, for the sine function, for the values of x, 0, pi over 6, pi over 4, pi over 3, all of these special angles from 0 to 2 pi, these right here are order pairs. The order pair 0, 0. The order pair pi over 6, this one right here, pi over 6, 1/2. The order pair pi over 4, root of 2 over 2, which is somewhere here. The order pair pi over 3, which is root of 3 over 2. and pi over 2, which is 1. That's the maximum value attained by the sine function for now. Of course, if these trigonometric functions have coefficients in front that actually represent vertical stretching or shrinking, we'll see about those in a second. All right? And well, let me erase all this. There's something else I would like to do. So we will look at those transform functions now. This is something pretty cool that I would like to relate another way. So, like I mentioned before, these trigonometric functions are usually called wave functions, oscillating functions, but maybe you heard about circular functions. All right? You might have heard of circular functions. Well, and the reason to that is because, well, we relate this to the circular functions like this. For example, what happens between 0 and pi over 2? Doesn't that go like this? It goes up, increases between 0 and pi over 2, and then decreases between pi over 2 and pi. That's a decrease, and then keeps decreasing between pi and 3 pi over 2, and finally increases again between 3 pi over 2 to 2 pi. So if we were to relate these points, the zeros, the maximum and the minimum, they just go around the circle. That's why we call them circular functions. And again, that's because for any angle, your favorite angle, say this one, add 2 pi, add one rotation to get back to the same point, add another rotation to get to the same point, keep adding rotation to get to the same point, etc., etc. All right? If we were to subdivide this into regions, check this out. So between 0 and 2 pi, we have this region of the sine function. All right? And let's use a different color. Between pi over 2 and pi, we have, between pi over 2 and pi, this region. And then let's use green. Between pi and 3 pi over 2, we have this region right here. All right. And last but not least, blue, between 3 pi over 2 and 2 pi, we got this region right here, the one that lies in the 4th quadrant. So you can think of a circle divided into 4 pieces, and then you cut half of it and you flip it to the other side. All right? So that's one way to see these trigonometric functions. And well, so let's look at the graph of the cosine function. Well, the graph of the cosine function has well, in this case, evaluate the cosine function for all the different angles, and so cosine of 0 equals to 1. Notice how this function, the graph of cosine starts at 1. All right, and then, well, for pi over 6, that's root of 3 over 2. How it starts decreasing instead, increases. So first decreases and then increases, as opposed to the sine function that first increases, then decreases, and increases once again. All right? Well, and all these points that are here, those are the key points based on the reference angles, on the most popular angles, which are the 30, 45, and 60 degrees, 90 degrees, and of course their corresponding multiples within a period of 2 pi. Then of course you can do 2 pi, do the next one, 2 pi plus that'll be 13 pi over 6. That's the same as going back to, what's that? To this point, pi over 6. But that's after a period up to pi. All right? And well, let's talk about the domain and the range. Well, the domain and the range, they're both negative infinity to positive infinity, and the range is negative 1 to 1 for both. Of course, when we get to the tangent and cotangent, the remaining trigonometric functions, well, that's going to change a little bit, right? So, okay. Characteristics of the graphs of sine and cosine. The domain, again, for both negative infinity to positive infinity. Okay, that's one. Let's put a check mark on that one. The range goes between negative 1 and 1. The period is to pi, that is, the graph, the shape of the graph repeats every 2 pi units. Now, here's where we see the differences. So, the first 3 points are the characteristic they both share. That is the domain, the range, and the period. However, the graphs right here, the sine function is symmetric with respect to the origin, and that makes it an odd function, as opposed to the cosine function, which is symmetric about the y-axis, which makes it an even function. All right? The graphs of y equals sine and y equals cosine differ by a horizontal shift of pi over 2. Let's see about it. Let me see if I can do that on the graphing calculator. All right? I think this is because, well, if you compare the shapes of the sine and cosine function, they are both the same, except that, okay, second table set. Let me go back to the default settings. Y equals sine x, cosine x, and okay, let's graph both functions. Well, I need okay, let me do zoom. No, not zoom, actually. It's window between 0 and second. Oh, no, not second, 2 pi. No. 0 and 2 pi. With scales of, how about, I'm going to do pi over 2 just to make it easy. Second pi over 2 and graph. Well, notice the two functions right here. Well, let me change the range to go, instead of negative 10 to 10, negative 2 to 2 and graph. What happened here? Negative 2 to 2. Much better. Did you see how essentially we have the same function? They're just shifted 90 degrees. So for example, check this maximum point on the sine function occurs when 90 degrees or pi over 2. The maximum point on the cosine functions is shifted 90 degrees from the maximum point of the sine function. Well, we can do a shifting cosine x minus second pi over 2. Let's shift it to the right, pi over 2 units, and see what's going to happen. They're going to overlap. All right? And that's because, well, that's the shifting, the 90-degree angle shifting in this case. And let's see. So let me go back to the paper. Yeah. So let's put a check mark on that one, because just verified it. All right. Now that we look at the generalized graph of the functions sine and cosine, what if we have something being multiplied by a in this case? Well, so number one, and that's something we covered at the beginning of the semester about shiftings and transformations of functions, all those horizontal and vertical shiftings, reflections about x-axis and y-axis, horizontal and vertical stretchings and stretch and compressions rather. Well, let's recall in general that the function y equals to a times f of x is the graph of f of x with a vertical stretch if the absolute value of the number that multiplies the function is greater than 1, and otherwise it's a vertical shrink, that is it gets a little smashed if the number is between 0 and 1. It's a number greater than 1 but less than 1, like a half, like a 1/3, etc. And we have a reflection across the x-axis if the coefficient is negative. And you might remember this uh, from y equals x squared, for example, whose graph is a parabola that opens up, as opposed to the graph of y equals x squared, or rather negative x squared, whose graph is a parabola opening upside down. All right? And well, same thing with trigonometric functions. I know there's like a big chapter or even 2 or 3 chapters about trigonometric functions, like they were special kinds of functions. Well, in fact, they are very special functions because we use these trigonometric functions to very particular applications in engineering, such as electronics and in environmental science when studying the waves, the motion of tides, for example. Those are modeled by trigonometric functions. Actually, I think we did one. No, we're going to do one example at the end of this section. One of those beach tides in this case. But the reason why we always go back and revisit these transformations is because these trigonometric functions, despite being so special, they also go with the same transformations as they go any other function like the parabola, etc. All right? So, how about we do some examples? Actually, for the in other words, I actually had something in mind. Oops, this is not what I meant. Let me move this over here. In other words, okay. And this is the mathematical, well, let me erase this actually. We don't need it anymore. In other words, so how can we summarize in words? All points in f of x, okay, for all points in f of x, multiply the y coordinate by the quantity a. That's all we do. So those 3 points that are listed above this statement summarizes into just multiply the y coordinate by whatever a value. Well, how about we see this in action, of course? Well, so graph the function and identify the key points on one full period. Okay, so this is what we're going to do. Number 1. For the very generic function, okay, let me do the sine function. Okay, let me do sine function on one full period, only one full period. Of course, you can extend this to more periods if you want, that's fine. Just make sure to keep adding multiples of 2 pi to the 5 key points. Yes, there's 5 key points. What are those 5 key points? Check this out. So I'm going to go between -1 and 1. All right, and let me draw a very generic sine function. And the very generic sine function looks like this. And where the graph completes one full cycle at 2 pi, half of the cycle is pi, a quarter of a cycle is pi over 2, and a third of a cycle, the third quarter of a cycle is 3 pi over 2. All right? So those are the 4 key points for the sine function. All right, let me make it a little smaller. Might need more space. Well, this is what I'm going to do. I'm going to list the 5, and guys, I recommend you write all these order pairs just so, I mean, I know it's kind of natural to just stretch the graph by 3 units about the x-axis, stretch it vertically, but in some cases, when it comes to doing this vertical shifting and then the phase shift, which is the horizontal shifting, you'll see how doing what I'm going to do is going to make more sense to graph even more complicated and more elaborate kinds of trigonometric functions. These are barely baby functions, and well, despite these being baby functions, don't underestimate them, okay? So that's the point 0, 0, that's the first point, the first key point. And then the second key point, isn't that pi over 2, comma 1? The third key point, that's pi over 0. The fourth key point, 3 pi over 2. Three pi over 2, comma, negative 1, and 2 pi. 2 pi, comma, 0. All right? What are we going to do with these 5 order pairs? Remember what I did in other words. Okay, multiply the y coordinate by a, and in this case a equals to 3, isn't it? So we're going to multiply the y coordinate by 3, by 3, by 3, and by 3, or another by 3. In some cases, yes, it's going to be a little silly because it's already a 0. 0 times 3, it's still going to remain 0. Yes, that's fine, but again, what I'm going to do here is going to help you a lot. You'll see how when we do the shifted versions of this, all right? When we do horizontal and vertical shiftings of this. Well, these are going to give us the resulting order pairs. Again, 0, 0, pi over 2, comma, 1 times 3, that's a 3. Pi, 0 times 3, which is 0. 3 pi over 2, comma, negative 1 times 3, careful, that's negative 3, and 2 pi, 0 times 3, that's 0. All right, let me do something about this. Let me make more room, because I'd rather have both on the same plane, both graphs. And so I need extra space. Let me move this also. Let me move this also, and I will extend this all the way to negative 2, negative 3, 2, and 3. All right? So, in this case, I'm going to go like this. I'm going to go like 0, 0. All right, that was the resulting point. 0, 0, it's still 0, 0. Pi over 2, 1 became pi over 2, 3. Pi 0 is still pi 0. And 3 pi over 2, negative 1 became 3 pi over 2, negative 3. And 2 pi 0, it's still 2 pi 0. I'm going to draw this by hand first. And see how this graph is vertically stretched by a factor of 3. In the same way that we did these kind of functions before, like in general, like a parabola, like a radical, like a reciprocal, etc. It's also the same for the trigonometric functions. Well, how about we see this on the graphing calculator? Well, let me increase the window to negative 4 to 4. Whoops. That way we can, okay, let me do sine, what was that, sine, right? Sine, let me do clear, let me do 4, oh no, actually 3 sine x, and graph. Do you see that vertical stretching? on the graphing calculator, same key points. All we did is multiply the y coordinate by the coefficient a. Well, that's one of the guidelines. Well, that's for what we call the amplitude, which we will define not today, but next time for sure. And what else? Of course, well, that's the first shifting and transformation for the trigonometric function.